We're gonna try. Let's try to rotate a molecule and make it anti-periplanar to do an E2 reaction. So we're gonna do an E2 reaction, and the tricky part is gonna be we're gonna need to rotate things so that they become anti-periplanar. Like this. So you look at this, and the first question we always ask ourselves is, what type of alkyl halide do we have? We have a secondary alkyl halide. So the other big clue here is I'm going to use a really bulky base or a bulky nucleophile. So if it's a bulky nucleophile that's reactive, we should be thinking about E2. Right? So reactive has an electron density. The problem is we also know for E2 we need the bromine and the H to be anti-periplanar. Right? We need them to be 180 degrees apart. Right? Because that's where sigma star is at. That's how we form that pi bond. We need the sigma star here for this carbon-bromine bond lined up. So when these two electrons move over, or they don't really move completely over, but when they attack sigma star, we form that pi bond there, as our base attacks the H, and our bromine leaves. So we need to be anti-periplanar to get the orbitals lined up. That's the key. The problem is, as we have it right now, this is not lined up. And the way I like to line it up, I like to put, just like I have it here, the H and the leaving group in the plane. So not the wedges and hatches. I like to put the leaving group and the hydrogen on the beta carbon in the plane. Because then it's easier for me to see what type of alkene I formed. Because we can form both E or Z alkenes in these cases. So it is important to know, get things anti-periplanar to see what type of alkene we form. So we need to rotate about the bonds. So if I call this, we'll call this the beta carbon, and we'll call this one the alpha carbon, The alpha carbon has the functional group bond to it. When we do eliminations, we always want to look for beta H's. There are other beta H's, There's beta hydrogens out here as well, but we're not going to use those. Why? No, they can still be anti-periplanar for sure. But the product we formed wouldn't be the most substituted. Remember Zaitsev's rule. The most substituted alkene, according to Zaitsev's rule. We could form a double bond here too as well, just to be fair. But according to Zaitsev's rule, we'd rather form the more substituted. This would be a tri-substituted versus a mono-substituted alkene. So let's do a rotation. I like to rotate one carbon at a time. Some people can do more than one. I like to do one at a time. So I'm going to say rotate, I'm going to say C beta first. So that means I need to get the H up here in the plane, That's where I need to get it. So to do that, I like to draw the H already there in the plane, the spot it needs to be. So there's in the spot. So if I do that, if you look at this, if this comes up, that means this methyl had to go back. So it's now hatched. And the isopropyl, this piece, has to be coming out at us. And the other part didn't change. Now, you can use model kits absolutely to help you with this. I highly recommend it. Don't be afraid to use your model kits for this. Basically, you take your R and S molecules and bring them together, and you can form like this sawhorse kind of thing, it looks like.
So would that change the stereochemistry then?
It won't change the stereochemistry, We just rotated. We're not shifting R or S. We're just looking at the vantage point. We're getting things lined up, anti-periplanar. So we're not changing R or S. We're just rotating, Because sigma bonds, remember, we can rotate about sigma bonds without breaking them. So now we need to do one last rotation. So we rotated about the beta carbon. Now we want to rotate about the alpha carbon because now we want to get the bromine in this position in the plane. So the part that didn't change, just draw that in. let's put the bromine where we want it, right? So if we bring this bromine down, what's going to be going, the H then is going to be going away from us, which then means the methyl is now coming at us. And now we're lined up, anti-periplanar. Now once we're lined up, now it's just the E2 mechanism that you know. Attacks, 2 electrons, we can say it goes to that carbon, goes there. And then the product we form, I like to draw, what I do first is I just draw the alkene. And then I look back at my starting material, the starting material here, and I see that this group and the methyl, the isopropyl here, the methyl are both on the same side. So I gotta make sure I draw those on the same side. I also look back and see this methyl here and this H are on the same side. They're both going away from us. So they also have to be on the same side. Right? And also remember, be careful, right? The isopropyl and the methyl are on the same carbon. Don't start moving things around. Right? But the methyl and the H are on the same side here. Isopropyl and methyl on the same side here. There's your E2 product. Right? You'd also have this alcohol and Br minus, remember, to balance the charge out. So then there's just a point of clarification, right? You'll want to draw these electrons from this hydrogen going to this carbon, right? When I draw it up here, I'm just showing you the molecular orbital picture. It's a more complete picture than you necessarily need. On sapling or on the test, you can just do it like this. I mean, if you want to draw the sigma stars in all the time, by God, all means do it. But you don't have to. In sapling, a lot of times you're just going to want these electrons to go to that, attacking that carbon to form this new pi bond. So if we're talking about solvent, so let's say we're in a polar protic solvent. In a polar protic solvent, right, if they're asking you what's the best nucleophile, right, the first rule always applies. The more electron rich and reactive you are, you're going to be a better nucleophile. So if you have a negative charge, you're always going to be a better nucleophile. Always. Right? So if you compared a carboxylic acid to its carboxylate, right? This carboxylate is always going to be the better nucleophile, no matter what. Now, let's say you're comparing this carboxylate to this guy. Right? So what have we changed? We've changed from oxygen to sulfur. Well, okay. What's different between oxygen and sulfur? If we look at the periodic table, sulfur is lower down. The same period, but lower down. So sulfur is bigger. So in a polar protic solvent, right, the solvent is able to interact with the nucleophile. Right? So the bigger the nucleophile is, right, the harder it is to surround. So in this case, in this polar protic solvent, this would actually be your best nucleophile. Right? Just because it's bigger and it's harder to surround with a polar protic solvent. Now, if you change the solvent, you would change who's number one. Right? If all of a sudden now I'm using DMF, now the best solvent, or the best nucleophile is going to be this, a carboxylate, because now the solvent's not really playing a role in messing with our nucleophile. So now the smaller the nucleophile, the more reactive it'll be, right? Because you could think about it this way. Sulfur's bigger, it can spread the charge out more. So that makes it more stable, less reactive, right? So the solvent's not playing a role, then it's about the smaller nucleophiles are more reactive. Let's go through maybe an allylic alkyl halide. Something like this. So the first question we always ask ourselves is what type of alkyl halide we have. So in this case we have a primary allylic. So the next question we have, once we know we have primary allylic, we know that can be SN1 or SN2. And we also should look at this and say, could it be E2 if we really want to get crazy? But for an E2 reaction to take place, we also need to have what needs to be available? Beta hydrogens, right? And now that we can get, I could get a little tricky with you guys, but I'm not going to. But there's no beta hydrogens here, right? As it stands.
Well, are you saying technically? So there's
Yes. There is no beta hydrogens.
Thank you. That's
But there are delta hydrogens, and those we could do a cascade reaction, but I'm not going to go there. Alpha, beta, gamma, delta, right? So there's no beta, so we're not worried about E2. Okay? So let's do two pathways. So it could be SN1 or SN2. Let's do the SN2. So let's do a good nucleophile, right? Because if we have a primary allylic, we either say SN1, SN2, and we say next question we ask ourselves is what type of nucleophile do we have? Do we have an electron-rich reactive one or a less reactive one? So if I'm telling you SN2, we want an electron-rich reactive one. So I'm just going to go with methoxide. Right, I'm not going to draw the mechanism out. Hopefully we can do this in our heads. It's one step. If it was a stereocenter, we'd have inversion, but the carbon attached to the chlorine is not RS, so it's not a stereocenter, so we don't need to worry about that. Right, and we also would have made what? We'd made Cl minus, right, to balance our charge. Hopefully we can do that mechanism in 2 steps. I'm not going to redraw. Now, what if we wanted to do an SN1? So we'll write SN1. What kind of nucleophile or solvent, usually in SN1, do we want here? We want a less reactive. So if I want to get the same type of product, I would use methanol. Now, SN1 reactions go through what kind of intermediate? A carbocation. If you have a carbocation, what can carbocations always do? Rearrange, right? Hydride shifts, methyl shifts, pi bond resonance. All right, so let's look at the first step. So I will draw the mechanism for the SN1. And I'm going to number my carbons because that's what you do, as your professor asks you to. Right? The first step is carbocation formation. Nope. I changed the nucleophile to be less reactive, just methanol instead of methoxide. I'm going to draw I'm going to go ahead and draw this carbocation twice because I think I'm going to have to use it twice because there's going to be a resonance structure. Well, here, I'll renumber. 1, 2, 3, 4, 5, 6. Can I draw a resonance structure for this? Hope so. Right, I can move these electrons there. And put a plus charge on carbon 3. So now we have 2 different intermediates, which probably means we can form 2 different products. Yeah? So I'm going to redraw the one. I'm going to redraw this one over, just because I don't like to have arrows, multiple arrows, coming and going from the same thing, right? Either should you. 1, 2, 3, 4, 5, 6. Same nucleophile for either case. Alright, so the methanol around. More of an interesting question maybe this is a little more advanced, but if I drew these as A and B intermediates, which intermediate's more stable?
B.
Why B?
Tertiary.
Tertiary carbocation, absolutely.
Or
No.
Oh.
Nope. Zaitsev matters for the final product. So, right, it's going to be an interesting thing just like we did in lab, where just because you have the most stable intermediate, does that mean you lead to the most stable product? No. Right? Tertiary carbocation, tertiary allylic carbocation is more stable than a primary allylic carbocation. But the tertiary allylic carbocation is not going to lead to the most stable product because of Zaitsev's rule. Whoa.
So Jacob's rule doesn't
So-
apply only to the.
Zaitsev's rule applies to final products, right? not to necessarily the carbocation intermediates. Right? So this is one of those situations where we can say we have a thermodynamic product, right, which is the most stable product. We also have a kinetic product, which comes from the most stable intermediate. So,
That would be a good question.
Yeah, why don't you ask this one?
I'm going to ask this question on the quiz tomorrow.
Thank you.
Whoever watches this later tonight will know I'm going to ask this question on the quiz tomorrow. Make sure you say something to me at the beginning of class that you watch this video, and I put this exact question on the quiz tomorrow. Okay, so the products, I'm not gonna fully do the mechanism because you guys should know that, because I know they've been doing that in sampling. So the products would be, and so it's a couple steps. One product would be exactly the same as the SN2 product, but you'd also get, right, after a couple steps, this other ether product, which is a good indication, right? When you see all of a sudden a rearrangement, you should automatically know in your head, well, that must have a carbocation intermediate, right? Because only carbocations rearrange, right? So when you see multiple products like this, you should say to yourself, there must have been a rearrangement going on. Because I know the SN2 reaction takes place in one step. Rearrangements aren't possible. So this is another good indication this was an SN1 mechanism. So looking at workshop number 2, and working at problem number 2, there's 2 eliminations essentially I've set up here. And one of the reasons why I know they're eliminations, right? In the first case, I know because I asked myself, the first question, of course, always is, what type of alkyl halide do I have? And I have a tertiary alkyl halide. So I know it can't be SN2. That still leaves the possibility for E2 now and SN1. So the next question we ask ourselves is, what type of nucleophile base do we have? And I look at this and I say, this is a reactive, electron-rich nucleophile base. And so I know it can't be SN1 then. So I'm stuck with E2.
So for SN1, does the base, does the nucleophile be small too?
No, for SN1,
Or did that
the nucleophile doesn't matter as much. The size of the nucleophile doesn't matter as much for the SN1. It's more about being less reactive. So if I know I have an E2, I start looking for beta hydrogens. All right, so there's beta H's here, and there's beta H's here. So I'm trying to figure out how many types of beta hydrogens there are. So in this case, how many types of beta H's are there? 2 types. We could say A, and we could say all of these are B. So if you have 2 types, that means each type will lead to a product, right? 2 different products. But in this reaction, we get a major product, and we have to decide what that major product would be. So let's number our carbons, 1, 2, 3, 4, and 5. So carbons 4 and 5 are the same, right? In an NMR carbon-13 spectrum, they'd be 1 peak. All those H's on carbon 4 and 5 would be 1 single peak, or actually a singlet worth 6 hydrogens in this case. So which beta H's are we going to take from which carbon? Are they going to take? We're going to take them from 4 or 5, or we're going to take them from 2? So we take it from 4 and 5, what would the product be? So let's look at what the product would be if I go through B. The product would be, the alkene would end up between which 2 carbons? The pi bond between which 2 carbons? If I took the hydrogen from 4. Between 3 and 4, let's say. Alright, so 1, 2, 3, 4, 5. Okay. So that was B, right? I'm assuming you know the E2 mechanism at this point. Let's look at what product A would look like. Where would the pi bond between, if I did beta hydrogens from A, the A beta hydrogens, where would the alkene be now, the pi bond? Between which 2 carbons? Between 2 and 3. 5, and the pi bond between 2 and 3. Anybody have any strong feelings about which alkene product we'd probably rather make? A. Why? It's trisubstituted, and according to Zaitse's rule, the more substituted the alkene, the more stable it is. So that's the product we're going to make, more likely to make. Okay, so the second part for 2 had this with our bulky nucleophile base. And so in this case, we have a secondary alkyl halide. So that could be, we know it can't be SN1, but it could be E2 or SN2. In this case, why might SN2 not be a good idea? Why might it be less likely? Because what's the big factor in SN2 always going to be? The bulkiness of bulkiness of the nucleophile, bulkiness of the alkyl halide, right? This nucleophile is pretty big, but also, yeah, this is a secondary alkyl halide, but right next door to it is a tertiary carbon with a bunch of carbons on it. So SN2 is probably going to be pretty tough, right? So let's think about E2 then. So then we go to E2 and we got to think about our beta hydrogens. So let's number our carbons. 1, 2, 3, 4, 5, 6. How many types of beta hydrogens? Which carbons have beta hydrogens?
Just one.
Just one. Good. Which one?
6.
6. Be careful. Carbon 4 does not have any hydrogens bonded to it. It has 3 other carbons. Again, why number your carbons? Because then you won't make this mistake. Because I guarantee somebody will think one of these is an H and try to do an elimination when there are no hydrogens there. And they'll have a carbon with 5 bonds to it. It'll happen. Promising. Prove me wrong. So let's draw an H in. This time I'll do the mechanism. Why not? Right? That's the only beta hydrogen there is. That's the only possible product then, right? So if it's going to react, this is the way it has to react. We don't need to worry about being anti-periplanar because, right, carbon 6 has 3 hydrogens bonded to it, so we're not going to have an E or Z situation. Also, there's no wedges or hatches, so obviously there's no inherent stereochemistry written there. So if I don't show it to you, you can't make it up, right? But we do know if we're going to make an alkene, we'd rather make an alkene that's E or Z. Z same side or not Z same side? Not Z same side. E, right? If we could, we'd rather make it E, right? But in this case, it doesn't matter because our pi bonds between which 2 carbons? 5 and 6. And we can't designate this E or Z because carbon 6 has 2 hydrogens. We can't rank those. One's not better than the other. So we just get this alkene. And, of course, Br minus and our alcohol. All right, so taking a look at the bonus from workshop number 2. Asking for a ring flip. So this is stuff you should have been able to do last semester. So going from everything that was axial becomes equatorial. Everything that's equatorial becomes axial. But if you're on the top of the ring, you're always on the top of the ring, right? That never changes, right? You can be axial up and equatorial up. Right? So if I draw this, and it turns out this will become important for some of these reactions, but this question itself is just asking you for a ring flip, which you all should still be able to do. And we'll practice tomorrow as well. So I'm just going to redraw what we have. And up and down. I'm going to number the carbons as I have numbered in the actual problem. 1, 2, 3, 4, 5, 6. I'm asking for a ring flip. So if we have the cyclohexane ring this way, to do a ring flip, 2 comes down, right? If 2 is like the headrest, 2 becomes the footrest, right? If you're a human sitting here, and 5 comes up and becomes the headrest. So I would draw it. You go the other angle, right? So 2 came down, 5 went up. So this is now 2, and this is now 5. So this would be 4, 3, 1, and 6. That's the first step. Okay, we all do that. All right. Pull down 2, bring up 5. All right, everything kind of slides over. Now you gotta start filling in what was on these carbons. So carbon 2 had a methyl group that was up and it was axial. So if it was up originally, it has to be up always. But it was axial. Now after a ring flip, it's gonna be equatorial. Right? Bromine here on carbon 1 was equatorial, but it was up. So now bromine needs to be axial, but it still has to stay up on carbon 1. Now carbon 6 has two things on it, both the same, so it's really easy. But you could look at it and say whatever, right, this methyl, if I labeled this methyl A and this one B, let's say, methyl A is axial and it's up, it needs to be up, but it needs to be equatorial in the other one. So there's A, and then B would now be axial down. But they always, if you're up, you're always up. If you're down, you're always down. But after a ring flip, if you were axial, you become equatorial. And this will become really important with some E2 reactions, SN2 reactions, and all these other ones as well. So we'll practice this tomorrow.